Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, becomes our gentle guide through starships, black holes, and the deep gravity of wonder. The most terrifying objects in the universe are not stars going supernova, not gamma-ray bursts raking across 1,000 light-years of space in seconds, not the cold, indifferent void between galaxies where no light has ever traveled and no light ever will. The most terrifying objects in the universe are black holes. Regions of space where gravity has won so completely, so absolutely and without appeal, that even light cannot escape. Where time does not merely slow, but stops. Where the known laws of physics, the equations we have written across centuries of careful observation and experiment, reach their edges and fall away into something we do not yet have the language to describe. A black hole is the universe keeping a secret. And yet, in the Star Trek universe, that optimistic, curious, endlessly hopeful vision of humanity's future among the stars, starships fly toward them on purpose. Captains give the order. Helmsmen engage the engines. And these great vessels, these cities among the stars, sail deliberately into the gravitational dark because something is always on the other side. Knowledge, survival, a crewmate who needs rescuing, a signal from home. Tonight, we are going to follow them. Hypnos guides you slowly through the vessels that dared to face the abyss. Through the real science, the genuine, peer-reviewed, Nobel Prize-winning physics that makes black holes the ultimate test of any starship, whether that ship is a fictional vessel of duranium and dream or a real spacecraft held together by mathematics and human ambition. We will move slowly. There is no urgency here. The dark between the stars has waited billions of years, and it will wait a little longer while we find our way into it together. You are on the bridge. The view screen shows stars, and somewhere ahead, hidden in the dark, a black hole waits. Let us begin. To understand what a starship is flying into, to understand the courage and the physics involved, we first need to understand what a black hole actually is. Not the vague, popular notion of a cosmic drain or a hungry void. The real thing, the thing the equations describe. It begins with a star. A massive star, something at least 8 or 10 times the mass of our own sun, spends its entire life in a state of perfect, terrible tension. The immense weight of its own mass presses inward, always trying to collapse. And the nuclear fires burning at its core push outward, always trying to explode. For millions of years, sometimes tens of millions, these two forces are perfectly balanced. The star shines. It fuses hydrogen into helium, helium into carbon, carbon into oxygen, building heavier and heavier elements in successive shells around an ever-growing iron core. Iron is where the fire goes out. You cannot fuse iron to produce energy. Iron absorbs energy. When the iron core reaches a critical mass, roughly 1.4 times the mass of our sun, packed into a sphere the size of a city, the outward pressure fails. In less than a second. Less than a second for a structure that has stood for millions of years. The core collapses catastrophically, falling inward at 1/4 the speed of light, and the outer shells of the star come crashing down after it. What follows is a supernova, one of the most violent events in the known universe. The outer layers rebound off the collapsing core and are blasted into space at 10% the speed of light. For a few weeks, a single dying star shines brighter than an entire galaxy. What remains at the center is either a neutron star, an object of almost incomprehensible density, a city's worth of mass packed into a sphere of pure neutrons E, or, if the original star was massive enough, something else entirely. A singularity. A singularity is what happens when the mathematics of gravity runs off the edge of the page. It is a point of infinite density, zero volume. All the mass of a dead star, sometimes many times the mass of our sun, compressed into a region so small that our equations simply stop working. We write the symbols, we do the calculation, and the answer is infinity. Infinity is physics throwing up its hands. Around this singularity, at a specific distance determined by the mass involved, lies the event horizon. This is the boundary. This is the edge. Inside the event horizon, the escape velocity, the speed at which you would need to travel to escape the gravitational field, exceeds the speed of light. And since nothing in the universe can travel faster than light, nothing can escape. Not gas, not particles, not light itself. You could aim a laser directly away from the black hole, fire a beam of photons at full speed, and that light would still be pulled inexorably back. It would arc inward. It would fall. Light falls. If you were to fall toward a black hole feet first, you would experience what physicists call, with remarkable casualness, spaghettification. The gravitational pull on your feet, slightly closer to the singularity than your head, would be measurably, catastrophically stronger. Your body would be stretched, pulled into a long, thin thread of atoms. The tidal forces, the differential in gravity across your body, would tear you apart at the molecular level long before you reached the singularity itself. This happens because gravity follows an inverse square law. Double your distance from a massive object and the gravity drops to a quarter. Halve your distance and it quadruples. Near a singularity, the difference in gravitational force between objects separated by even a few meters becomes incomprehensible. But here is something strange and beautiful. The size of the event horizon depends on the mass. A stellar mass black hole might have an event horizon just a few kilometers across. A supermassive black hole like Sagittarius A at the center of our own Milky Way galaxy has an event horizon millions of kilometers in diameter. And at the horizon of a supermassive black hole, the tidal forces are relatively gentle. You might cross the event horizon of Sagittarius A without feeling anything unusual at all. The singularity is still ahead. The interior is still one-directional, but the entrance, for a moment, would be almost peaceful. There is more. There is always more. Black holes can spin, and most of them do. When a massive rotating star collapses, it conserves its angular momentum, like a figure skater pulling in their arms. GRS 1915, 105. A black hole in our own galaxy completes over 1,000 full rotations every second. A spinning black hole does not merely distort space. It drags space itself along with it, twisting the fabric of space-time in a phenomenon called frame dragging. Around a rapidly spinning black hole, even empty space is in motion. And then there is the question of time. To an observer watching from a safe distance, something extraordinary happens as an object falls toward an event horizon. The light it emits becomes increasingly redshifted, stretched to longer and longer wavelengths by the intense gravitational field. The object appears to slow and slow and slow. It never actually crosses the horizon. Not from the distant observer's perspective. It simply freezes there, dimming, reddening, fading over billions of years, never quite gone. The person falling, of course, experiences something entirely different. They cross the horizon. They continue falling. They may not even notice the moment of crossing. But for them, looking outward, the universe's entire future plays out in an instant, compressed, blue-shifted, blazing, before the singularity ends everything. Finally, there is the information paradox, a question that has occupied the greatest minds in physics for decades. When matter falls into a black hole, what happens to the information it contains? The quantum states, the configurations of atoms, the fingerprints of what it was. Stephen Hawking showed that black holes are not entirely black. They emit a very faint thermal radiation, now called Hawking radiation, slowly evaporating over inconceivably long timescales. But does this radiation carry the information back out, or is it destroyed? Quantum mechanics says information cannot be destroyed. General relativity says it cannot escape. Both cannot be right. The universe is keeping that secret too. Against this backdrop, against the spaghettification and the singularities and the frozen light and the stolen information, human beings in the Star Trek universe built ships and flew them into the unknown. Let us meet them, not as props or plot devices, but as the extraordinary things they are, the accumulated dreams of engineers and dreamers given form and function and assigned to face the abyss. The first one was the smallest. The NX-01 Enterprise was launched in 2151, 225 meters long, warp 5.2, a crew of 83, no deflector shields, only polarized hull plating. Her captain was Jonathan Archer, who had spent his entire life dreaming of the stars while watching his father's warp engine work be delayed by politics and alien interference. The NX-01 was humanity's first deep space explorer. She built the relationships that would eventually become the Federation before the Federation existed. And she faced a trinary black hole system in an episode called Singularity, where exotic radiation flooding from the black hole's accretion disk drove her entire crew into states of obsessive madness. They nearly died cataloging chair specifications and perfecting dinner recipes while the ship drifted toward annihilation. T'Pol, whose Vulcan physiology gave her some resistance to the radiation, navigated them out alone. A small ship, a small crew. The first time human beings flew toward a black hole and came back. The Constitution-class USS Enterprise, NCC 1701, 289 meters long, warp factor 8, launched 2245, was James T. Kirk's ship. The one that made us believe, with something deeper than mere intellectual agreement, that we could go anywhere in the universe and face whatever was there and come home again. The original, the standard against which every starship since has been measured. The Constitution refit NCC 1701A 305 meters was the movie-era evolution. This was the ship that faced V'ger, a living machine of incomprehensible scale and power, born when Voyager 6, an ancient NASA probe, passed through what they described as what they used to call a black hole. It emerged on the far side of the galaxy, was found by a planet of living machines, and was enhanced beyond all recognition. The black hole as transformation, as rebirth into something unrecognizable. The Excelsior class, NCC 2000, entered service with great ambition. At 467 meters, the largest Starfleet vessel of her era, She was built around a transwarp experiment that ultimately failed. But the ship itself was extraordinary. She became the workhorse of the fleet for a century, a testament to sound engineering over speculative innovation. Sometimes the steady ship is the survivor. The Galaxy-class USS Enterprise, NCC 1701D, was something different. 642 meters long, 42 decks, a crew of over 1,000 people, not soldiers only, but scientists and diplomats and children and families living their lives among the stars. This was the ship that dared to say that the future of space exploration was a civilization, not a military operation. Jean-Luc Picard commanded her. She faced the Borg. She was the diplomat of starships, but she was also, when she had to be, a warrior. The Intrepid-class USS Voyager, NCC 74656, 344 meters, variable geometry warp nacelles, a crew of 141, maximum warp 9.975 E, was designed for deep space exploration and ended up fulfilling that purpose against her will. Hurled 70,000 light-years to the Delta Quadrant by an alien entity, she spent 7 years finding her way home. Every black hole she encountered on that long journey was a potential shortcut or a potential end. Voyager's relationship with black holes was intimate and ongoing. She used them. She survived them. She looked into the event horizon and kept flying. The Defiant class, 170 meters, was the ship Starfleet never wanted to build, an escort vessel, a warship, designed during the darkest years of the Dominion threat. Overpowered engines on a tiny, heavily armored frame. She was not built for exploration. She was built for survival. The Sovereign class, USS Enterprise, NCC 1701E, was 685 meters and warp 9.99 and the closest thing Starfleet had ever built to a predator. She faced the Borg in their cube and won. She was the ship of a changed Federation, one that had learned that optimism needed to be armored. And the Inquiry class, 470 meters, over 200 vessels built in response to a galaxy grown more dangerous than anyone wanted to admit. The fastest and most heavily armed Starfleet vessel produced in quantity, built quickly, built well, built for what was coming. These are the ships that face the dark. Let us follow them into it. The story of Star Trek and black holes is almost as old as Star Trek itself. Let us travel through it, slowly, chronologically, letting each encounter breathe. 1967. Tomorrow is yesterday. The original Enterprise encounters a black star. The episode predates the widespread popularization of the term black hole by several years. John Wheeler would coin the phrase in a lecture that same year, but the writers of Star Trek were working from the same intuition, that dead massive stars create regions of impossible gravity. Kirk uses the gravity of this black star to accelerate the Enterprise to a velocity high enough to break free of the normal flow of time. The ship slingshots around the dark mass and emerges in 1969 over Earth. The slingshot maneuver, the deliberate use of a massive gravitational body for speed, for escape, for time travel, would become Starfleet's signature move. Kirk used it again in the voyage home. Pike would use it centuries later, in a very different crisis. 1973. Beyond the Farthest Star, the animated series. The Enterprise arrives at a dead star, a mass so old and cold it has collapsed into near invisibility. Trapped in its orbit is an ancient alien spacecraft, vast beyond imagining, and within it, an intelligence imprisoned in the gravitational embrace of this dead star for hundreds of millions of years. Desperate, malevolent, it wants out. It wants to use the Enterprise as a vehicle for escape. Kirk refuses. They leave the intelligence where it is, in orbit around its dark prison, and the Enterprise pulls away. The episode lingers. That intelligence waiting, circling for millions of years, a prisoner of gravity in the dark. There is something in that image that touches something very old in us. The fear of being trapped. The fear of waiting in the dark for something that never comes. 1979. Star Trek, the motion picture. The V'ger cloud arrives, larger than some solar systems. A living machine. It destroys 3 Klingon battlecruisers the way you might brush away flies. Voyager 6, an old NASA probe lost in space, had at some point passed through what they used to call a black hole. What emerged on the other side was not the probe itself, or not only the probe. It emerged on the far side of the galaxy, near a planet of living machines who found this primitive device and could not understand why it had not yet completed its mission: to learn all that can be learned and return that knowledge to its creator. So they enhanced it, built it a vessel, amplified its capabilities beyond all human comprehension. V'ger had crossed a black hole and become something like a god, the black hole as doorway, as passage between one kind of existence and another. In the real universe, we do not know what lies on the other side of a black hole's singularity. The mathematics suggests a second universe, or a different region of our own, connected through the singularity like a bridge. Star Trek's V'ger is a poetic vision of what a journey through that bridge might produce. Transformation so complete that what emerges is unrecognizable and incomprehensible and lonely. 1995. Parallax, Voyager's second episode in the Delta Quadrant. They detect a distress signal and locate another ship trapped near a quantum singularity. The captain orders an approach. They draw closer. The singularity's event horizon shimmers and reflects. It bends light, and in bending it, creates a mirror, a time-delayed reflection of the space around it. The ship they are approaching is themselves. Voyager, hours earlier, approaching the singularity for the first time. They are caught in a loop, seeing their own past selves through the distorted lens of a black hole's gravity. B'Elanna Torres, new to her role as chief engineer, realizes the truth. They need to find the original entry point, the crack in the event horizon through which they first arrived, and exit through it before it closes. Gravitational lensing, the bending of light by massive objects, is a well-documented phenomenon. We use it to study distant galaxies too faint to see directly, using intervening massive objects as natural telescopes. Near an event horizon, the lensing becomes extreme. Light orbits. Images multiply and distort. You might, theoretically, see the back of your own head. 1998. Hunters. The Hirogen are hunting Voyager across the Delta Quadrant. These are beings for whom the hunt is not a sport, but a religion. They have been hunting across the galaxy for thousands of years, and they are very good at it. The crew discovers a micro-singularity in the vicinity, a small black hole, its event horizon just kilometers across. In the hands of a Federation crew, even under duress, this becomes an opportunity. They weaponize it. Using a precisely calibrated energy burst, they expand the micro-singularity, creating a gravitational event powerful enough to threaten the Hirogen vessel. The hunters, for once, flee. A black hole not as obstacle, but as weapon. not as something to survive, but as something to deploy. The physics is fictional, but the impulse is very human. When the universe hands you a gravitational catastrophe, see if it can be aimed. 2002. Singularity. The NX-01 Enterprise, a trinary star system with a black hole at its gravitational center, something no human or Vulcan had ever seen at close range. The ship passes through a region of intense subspace radiation flooding from the black hole's accretion disk. Invisible. The crew does not know it is affecting them. What follows is slow, creeping horror. Each crew member begins to fixate obsessively on a single task. An officer struggles to perfect the captain's chair. Dr. Phlox cannot stop adjusting a patient's treatment. Chef perfects and reperfects his recipes. They are all working, all occupied, all productive, and none of them notice that the ship is drifting toward the singularity and that they have been drifting for hours. T'Pol, whose Vulcan neurophysiology gives her some resistance, realizes what is happening. She navigates the ship out alone at the limits of her own degraded faculties, and they escape. In the real universe, space is full of radiation, cosmic rays, X-rays from accretion disks, gamma radiation from pulsars. Black holes in particular produce some of the most intense radiation environments in existence. The idea that proximity to one might alter cognition is not entirely without precedent, even if the specific mechanism is fictional. 2009. Star Trek. Red matter. A single drop introduced into a planetary core ignites an artificial black hole from the inside out. The planet is consumed in minutes. Vulcan, 6 billion people, thousands of years of civilization, the birthplace of the logic and discipline that helped humanity become something better than it was, is gone, swallowed, crushed into a singularity. It is the most devastating use of a black hole in all of Star Trek, not because of the physics, but because of what it destroys. Nero, a Romulan miner from the future, weaponized a phenomenon that the universe uses to create and recycle matter and turned it against a world. At the end of the film, Spock uses the last of the red matter to stop Nero. The Narada is swallowed. Spock's ship, the jellyfish, is caught in the gravity well. Both vessels are pulled back through time to 2233, the year everything changed. The black hole as genesis, as destruction, as door between versions of reality. 2019. If memory serves. Star Trek, Discovery. Michael Burnham and Spock arrive on Talos 4. The Talosians, ancient beings of immense telepathic power, greet them with a test. They show Burnham and Spock a black hole, a realistic one, the glowing accretion disk, the photon sphere, the gravitational shadow at the center bending light around it in a perfect, terrible halo. And they fly into it. They cross the event horizon. They fall, and they break through, because it is an illusion. The Talosians created it to test the strength of their perception, their ability to know reality from constructed experience. A black hole as trial, as the ultimate test of whether you trust what you know over what you see. 2022. Memento Mori. Strange New Worlds. Captain Pike's Enterprise. A Gorn destroyer is hunting them. A black hole nearby is slowly consuming a brown dwarf companion, drawing stellar material off in a long, luminous stream into the accretion disk. Pike orders the ship into the gravity well, using it to slingshot away from the Gorn, The same move Kirk made in 1967, refined for a new century. But then he has a device detonated in the accretion disk, creating a burst of radiation and debris that mimics the electromagnetic signature of an exploding starship. The Gorn believe the Enterprise has been destroyed. The black hole provides cover, camouflage, the greatest possible noise in which to hide. 2024. Lagrange Point. Star Trek Discovery. The final season. The progenitor technology. The legacy of the ancient species that seeded life throughout the galaxy is hidden in the last place anyone would look, between two black holes. A Lagrange point is a real phenomenon, a location where the gravitational forces of two massive bodies precisely cancel each other. In this episode, the technology is hidden at the point between two singularities where their immense gravity cancels to zero, a needle threaded in the absolute dark. The Discovery must navigate between twin event horizons, riding the balance point to reach what has been left for them. Not a threat to be escaped, not a weapon to be deployed, a hiding place, a place so dangerous that only someone who truly needed to find what was hidden would risk the approach. None of these ships should have survived. By the physics of our universe, every one of these encounters should have ended in destruction, spaghettification, radiation death, tidal dismemberment, the slow freeze at the event horizon. But they survived, and the technology that saved them is worth understanding, even in its fictional form, because some of it is closer to real possibility than you might expect. Structural integrity. Fields are invisible force fields reinforcing every surface of a starship. Every bulkhead, every deck plate, every strut and beam in the vessel's skeleton. Without them, the structural stresses of warp travel alone would tear any ship apart within minutes. Near a black hole, these fields are pushed beyond their rated limits. In episode after episode, you hear the chief engineer calling out the numbers. IF at 115%, at 120, at 130. The fields are holding, but holding by diminishing margins, and every 0.1% is another heartbeat of survival. The underlying principle, using energy fields to counteract structural stresses, is not impossible in kind. We use electromagnetic fields to contain plasma in fusion reactors. We use magnetic fields to shield spacecraft from radiation. The extension of these principles to something that could reinforce matter against tidal forces is an enormous technological leap, but it is a leap in a direction that physics does not forbid. Inertial dampeners are the unsung heroes of Starfleet engineering. Without them, any starship crew experiencing rapid acceleration would be instantly killed. The human body can tolerate perhaps 9 Gs briefly with training and equipment. A warp jump produces effective acceleration that would register in the millions of Gs without dampening. Near a black hole, the differential gravitational acceleration across the ship's length, the spaghettification gradient, is the thing that kills you, and the inertial dampeners are fighting to maintain exactly 1 G of comfortable, habitable gravity for every crew member at every point in the ship. When the dampeners fail, and in crisis situations, they always threaten to. The first sign is crew members being thrown across rooms. The second sign is death. The deflector dish is the most versatile piece of technology in the Star Trek universe, which is saying something for a universe that includes transporters and replicators. Its primary function is mundane, sweeping interstellar medium out of the path of a ship traveling at warp, where even a hydrogen atom would strike with the energy of a torpedo at sufficient velocity. But in practice, the deflector has been used for almost everything. Graviton pulses to counter gravitational gradients, anti-graviton beams, inverse tachyon beams that briefly opened a quantum fissure in space-time, verteron pulses, antiproton beams, metaphasic shields, subspace field generators. The deflector dish is Starfleet's answer to, "We can't possibly survive this." The answer is always, yes we can. Modulate the deflector. The warp drive, at a fundamental level, does not propel a ship through space. It distorts space itself. A warp bubble is a region of contracted spacetime ahead of the ship and expanded spacetime behind it, creating a wave that the vessel surfs. Inside the bubble, the ship is, in theory, stationary. The bubble is moving and the ship is inside it. This is the same principle, the Alcubierre metric, proposed by physicist Miguel Alcubierre in 1994, that real physicists have studied as a theoretical basis for faster-than-light travel. The math works. The energy requirements are preposterous by any current standard, and there are significant unsolved problems. But the concept is grounded in genuine general relativity. And here is why it matters for black holes. If the warp bubble creates a region of locally flat spacetime around the ship, then the ship inside the bubble is insulated from the curvature of the spacetime around it, including the curvature created by a black hole. The battle in every Trek black hole encounter is between the warp field and the gravity well. The warp engines fight the singularity, and usually, barely, always barely, the warp engines win. The slingshot maneuver, stripped of warp physics, is real engineering. Gravity assists are the standard method for accelerating spacecraft to high velocities without burning enormous amounts of fuel. The Voyager probes used Jupiter and Saturn for gravity assists and are now the fastest human-made objects in history. The math is a beautiful interplay of orbital mechanics, and it works every time. In the Trek version, a ship traveling near warp velocity uses a gravity gradient to bend its trajectory and add velocity, sometimes enough to break through the time barrier, which the show posits as a real physical phenomenon at extreme relativistic speeds. Kirk used it around a black star. Pike used it around a black hole with a brown dwarf companion, and then used the cover of the accretion disk to vanish. The maneuver is always risky, always precise, always the kind of flying that requires a very good helmsman and a captain willing to bet everything on the math. The real universe does not have warp drives or structural integrity fields or deflector dishes, but the real universe does have black holes. And what we know about them, what we have actually measured, actually imaged, actually confirmed, is stranger and more wonderful than anything Star Trek has imagined. Kip Thorne is a physicist who has spent his career on the edge of what general relativity permits. He shared the Nobel Prize in 2017 for the detection of gravitational waves, ripples in space-time, caused by the collision of two black holes 1.3 billion light-years away. He also served as the scientific advisor for Christopher Nolan's Interstellar, which attempted to depict a realistic black hole for the first time in cinema history. The accretion disk rendered for that film, the way it curves up and over the shadow of the black hole due to gravitational lensing, was not artistic license. Thorne's team calculated it from first principles. Star Trek Discovery, in its later seasons, began adopting this visualization, rendering black holes as they actually appear. Sagittarius A is the supermassive black hole at the center of our own galaxy, 4 million times the mass of our Sun, 26,000 light-years from Earth. For decades, we knew it was there because of its effects on the stars orbiting it. Stars moving in tight ellipses at enormous velocities, their orbits only explicable if something of immense mass lurked at their center. In 2022, the Event Horizon Telescope, a global network of radio observatories linked together to form an Earth-sized telescope, produced the first image of Sagittarius A. What we saw was a glowing ring, a circle of bent light, photons from superheated gas in the accretion disk, bent around the black hole by its gravity, forming a luminous halo around a shadow. The shadow is the region where light cannot escape to reach us. The ring is photons that almost fell in, but were bent just enough to arc around and reach our detectors. It looked exactly like what the equations predicted. Time dilation is not science fiction. It is an engineering problem we deal with every day. The GPS satellites in Earth's orbit experience two opposing relativistic effects. They move fast enough that their clocks run slow relative to Earth, but they are farther from Earth's gravity well, so their clocks also run fast relative to ours. The general relativistic effect is larger. Without correction, your GPS coordinates would drift by kilometers per day. Your phone corrects for Einstein's equations every time you ask it for directions. At the event horizon of a black hole, the time dilation becomes infinite. An external observer watching someone fall toward the horizon would see them slow and slow and slow, never quite reaching it, their light red-shifting toward infrared and then microwave and then nothing over billions of years. The infalling person, meanwhile, crosses the horizon in finite time and continues falling. Both observations are simultaneously correct. Time is not universal. It is local, personal, dependent on where you are in a gravitational field. Wormholes emerge from the same equations that produce black holes. The mathematics of general relativity permits, does not require, but does not forbid, a connection between two distant points in space-time through a shortcut in a higher spatial dimension. An Einstein-Rosen bridge. Star Trek uses wormholes constantly. The Bajoran wormhole in Deep Space Nine, the Barzan wormhole in TNG. The distinction between a black hole and a stable wormhole is, in the mathematics, a matter of exotic matter, negative energy density, holding the throat open. Whether exotic matter exists in sufficient quantities for this purpose is one of the genuinely open questions in theoretical physics. Could a starship really survive a black hole? With known physics, no. The tidal forces at the event horizon of a stellar mass black hole would destroy any material object. There is no known material strong enough. But a supermassive black hole is different. With an event horizon millions of kilometers across, the gradient of gravity across a starship's length is relatively mild. You could, in principle, cross the event horizon of a supermassive black hole without experiencing any dramatic effect, at least at the moment of crossing. Once inside, every possible path through space-time leads toward the singularity. There is no sideways. There is no backwards. But the entrance would be, for a moment, almost peaceful. Star Trek hand-waves the interior with deflector dishes and structural integrity fields and warp drive. In doing so, it is not being lazy. It is being aspirational. It is saying, given technology we cannot yet imagine, given understanding we do not yet possess, what would we do? Where would we go? The answer in every series, across every decade of storytelling, is the same: straight into the dark. Not every ship comes back. The story of Starfleet's encounters with black holes is also a story of loss, of ships consumed, of civilizations destroyed, of timelines altered beyond repair. Let us pause in that darkness and acknowledge the cost. USS Voyager was not lost in the conventional sense. She returned. But she was lost to the Delta Quadrant for 7 years. 7 years of her crew's lives. Years they did not spend with families on Earth. Years that passed in the distant, alien dark 70,000 light years from home. Every black hole they encountered on that long journey was a potential shortcut or a potential end. Every quantum singularity was a threat and an opportunity simultaneously. The crew that stared into event horizons and refused to blink. The crew that learned to think of the Delta Quadrant not as a prison but as their ocean, and navigated it accordingly. The Narada was swallowed by a red matter black hole in the alternate timeline, a mining vessel that had been in the wrong place at the wrong time, watching Romulus destroyed by a supernova, and had bent its grief into a weapon. Nero and his crew emerged from the black hole over a century in the past. They had been inside for 3 years of their subjective time. What they found when they emerged was a universe they recognized but could not yet harm, one where Romulus still stood, where their homeworld was not yet ash. They waited, they planned, they changed everything. A black hole swallowed a grieving man and spat out a monster, not because of any quality of the black hole, but because of what grief can do to a person in the absolute dark. Vulcan. 6 billion lives. A planet that had stood for tens of thousands of years, that had given the Federation its commitment to logic and reason and the discipline of mastering one's own worst impulses. Consumed in minutes by an artificial singularity ignited in its core. In one universe, the planet stands. In another, it is nothing but light bent around a memory. The survivors, a few thousand Vulcans who were off-world when the planet died, became a people without a world. They settled New Vulcan. They rebuilt their culture in exile. Spock continued to serve, continued to explore, continued to fly toward the dark, because that was who he was. What does it say about a people, about a civilization, that even after the greatest loss in their history, the response is, we continue, we fly, we explore, we face the next black hole and the one after that. The USS Enterprise C was an ambassador-class ship. She was lost at Narendra 3, defending a Klingon outpost from a Romulan attack, fighting to the last against overwhelming odds. Her loss was not to a black hole, but it bent history the way a black hole bends light. Her sacrifice created the conditions for the Klingon Federation alliance, an act of courage, once upon a time, radiating outward through decades of consequences. There are many kinds of event horizons, many kinds of points of no return. Not all of them are made of gravity. The cost of curiosity is real, and the universe does not forgive mistakes near a singularity. But the ships that faced black holes and came back, and most of them did come back changed. They came back with data, with understanding, with the knowledge that the boundary could be approached and survived, that the laws of physics, however extreme, were still laws, still comprehensible, still something a crew with enough intelligence and courage could navigate. That is the lesson. Not that the dark is nothing to fear. The dark is everything to fear. But fear is not a reason to turn back. It is a reason to understand. Why do we keep flying toward the dark? It is a genuine question, not a rhetorical one. Why, in story after story, Do the crews of Starfleet ships approach the thing that could destroy them? Why does every encounter with a black hole produce not just terror, but also wonder? Why, when the event horizon fills the view screen, do the crew members lean forward? Because a black hole is the ultimate unknown, the place where the map ends. Every navigational chart, every star catalog, every sensor reading becomes meaningless at the event horizon. Beyond that boundary, the instruments fail, the laws fail. Everything we thought we knew about how matter and energy and time behave fails. And on the other side of that failure, something else is. We do not know what. Physics has not told us yet. Hawking radiation whispers a clue, but the whisper is too faint for our current instruments to hear. The information paradox suggests that the universe keeps a ledger, that nothing is ever truly lost, that everything that falls in leaves some trace on the surface of the horizon, but we cannot read that ledger yet. The black hole keeps its secrets the way the deep ocean used to keep its secrets, the way the interior of continents used to keep their secrets, the way the far side of the moon kept its secrets until someone finally flew around it. And Starfleet's answer, from the NX-01 to the Discovery, from the original Enterprise to the 1701E, is always the same. We are going to fly straight at it and find out. The ships we have followed tonight are not defined by their length in meters or their maximum warp factor or their weapons loadout. Though we have noted all of these things, they are defined by what they are willing to fly into. The NX-01, tiny and fragile by the standards of what came after, flying toward a trinary black hole system with nothing but polarized hull plating and the courage of a crew that had no idea what they were doing, but was going to do it anyway. Voyager, alone in an alien quadrant, using a micro-singularity as a weapon, because that was what the situation required. Pike's Enterprise, threading the gravity of a black hole to vanish from enemy sensors, playing the universe's physics like a chess move. These are acts of imagination, but they are also acts of science. The slingshot maneuver is real. Gravitational lensing is real. Time dilation is real. Sagittarius. A star is real, and we have photographed it, and it looked exactly like the equations said it would. The warp drive is fictional, but grounded in a real mathematical solution to Einstein's field equations. The deflector dish is exaggerated, but the principle, using directed energy to counteract environmental forces, is something we do in smaller ways every day. Star Trek imagined a future in which human beings did not merely study the universe from a safe distance. We got into ships and we went there. We flew to the edge of the known and we peered over. We found that the universe was stranger and more beautiful and more terrifying than anything we had imagined. And we found that this was a reason to keep going, not to stop. Tonight, as you drift toward sleep, let yourself imagine the bridge. The lights are low. The night shift is on. A skeleton crew, competent and calm, the hum of the warp drive a steady vibration beneath the deck plating. The view screen shows a region of absolute darkness. Not the ordinary darkness of deep space, scattered with the distant light of stars. An absolute darkness, a place where light is absent, not because there is nothing there to emit it, but because everything that reaches that region is trapped, held, consumed. Around the darkness, a halo, bent light, gas and dust heated to millions of degrees, glowing in every wavelength from radio to X-ray, orbiting in a disk that blazes against the dark. Photons that almost escaped but did not, orbiting in the photon sphere, circling and circling, the universe's light pooling at the edge of the impossible. The captain gives an order. The helmsman, steady at the controls, engages the engines. The structural integrity fields come online. The inertial dampeners adjust. The deflector dish hums with a new frequency, something the engineers have just modulated for this specific gravitational gradient, this specific encounter. The chief engineer watches the numbers climb and holds her breath. The ship moves toward the dark. Not because it is reckless, not because the crew has forgotten what a black hole is, but because something is on the other side, knowledge or survival or a crewmate or home, and because the mathematics says they can make it through if they fly precisely and trust the engineering and trust each other. The bridge is quiet now, and the rhythm of the ship seems slow and even. The hum of the warp drive, that low, steady, everywhere sound, is the sound of velocity, of purpose, of a ship that knows where it is going and why. The darkness fills the screen. The ship is deep in the gravity well now, the event horizon ahead and the open stars falling away behind. The structural integrity fields are at 127%. The inertial dampeners are holding. The deflector is singing with a frequency no human ear can hear, but every sensor registers. And then, the maneuver. The warp bubble tightens. The gravity gradient shifts. The ship slides around the black hole's edge, the way water slides around a drain, close, impossibly close, using the gravity rather than fighting it. And then the engines fire, full impulse, full warp, and the ship pulls free. The event horizon recedes. The stars come back. Slowly, and then all at once, normal space surrounds the ship again. The halo of bent light grows smaller behind you. The accretion disk dims. The dark retreats. The captain exhales. The bridge exhales. The view screen shows stars, countless, ordinary, beautiful stars, each one a sun, each sun perhaps a center, each center perhaps a place where something lives and wonders and looks up at the sky. And behind you, already impossibly far behind, the black hole sits in the dark the way it has always sat, patient, immense, keeping its secrets, waiting for the next ship that is willing to come close enough to learn something. The vessel drifts onward. Let the stars blur and soften at the edges. Let the ship's hum carry you somewhere deeper. The black hole is behind you. The dark is not an enemy. It never was. It is an invitation. It has always been an invitation to wonder, to understand, to fly toward the thing that frightens you and find out that you can survive the approach. You have always been the kind of person who accepts that invitation. The ship keeps flying. The ship will keep flying. The crew will keep watch. The mathematics will hold. The universe is very large and very old and full of things we do not yet know. That is not something to fear in the dark. It is something to carry with you into it, and the stars remain.